How's everybody doing? Welcome. How's homework going? It looks like 6 of you guys have turned it in.
I did it all this morning.
Sweet. I mean, it shouldn't really take you more than like an hour or two. I just want to make sure nobody's having issues that hasn't reached out.
Yeah, I think I did what you asked for.
Cool. I am gonna try to commit to grading things in this class this time around. So I know I haven't done the first one yet, but I am gonna try to do all that this weekend. So hopefully you'll get some feedback fairly soon. I'm gonna share my screen. So I hope you guys all enjoyed Bill's presentation. I was talking to Mason earlier today, and I think the game plan is for us to basically try to implement almost everything he talked about for the rest of the quarter. So he covered a lot of really useful techniques. We have the hardware to implement that stuff and test it in a meaningful way on our panel. So that's kind of our goal, is the stuff he covered kind of sets a pretty good scope of what we should try to get through in terms of control. So we'll work on that more going forward. But right now, as I promised you at the end of last week, we're going to talk about piping and instrumentation diagrams, because some of you are in senior design and you might find this somewhat useful. So a P&ID. Ooh, that one is toast. I'm gonna get a new marker. So piping and instrumentation diagrams, P&IDs. Some of you have encountered this before in jobs. Some of you may have heard this before. Some of you may have never heard this before. But if you go into kind of a traditional process engineering role as a Chem E, you're going to be dealing with these a lot. And basically what this is for a defined scope of system, it covers all the major unit operations, all the major piping, and all the major instrumentation in a drawing set. So you might guess that from the name, piping and instrumentation diagram. So usually what this can be a single drawing, this can be a huge drawing set. And usually when you're dealing with these, it's going to fall within the scope of a plant. And so there will be existing drawing sets for the plant already that cover your utilities. God, I can't write and talk at the same time. All your major available utilities and services that you might tie into. And so what this will look like in a really like simplified diagram is like, let's say you have some kind of distillation column. So you'll have your column here, and then you'll have like steam, going to the reboiler at the bottom. This will get more detailed later. And then you'll have a condenser with chilled water going into the top, and you'll have like your feed stream from somewhere, and then you'll have your tops and your bottoms. And so, and this feed stream is coming from somewhere, and this top and bottom is going from somewhere, and then these utilities are coming from somewhere, right? And so if this is one, then you'd have like, not as part, so this set that we're talking about here deals with this distillation column, right? And then, so that would be part of set one, and that's your project set. And then over here, set two would deal with your chiller. Oof, that needs to be a C, not an S. So chilled water generator, and that goes out. And then you have a return. And so all of these, and then you basically have a reference from here to here. So you use a reference arrow like we drew on our other drawings previously to show that link. And those arrows again just have drawing numbers and maybe line quadrant numbers like we showed before. And so anytime you're doing a project at a plant, you're going to generate stuff from set one, and then you're probably going to reference a bunch of other sets for your utilities. And then you might reference other sets for your upstream and downstream operations that your product streams are feeding, or where your end feed comes from. So from that mindset, P&IDs are really similar to electrical drawings in the way they reference, right? It's basically just you need to know where your stuff's coming from, where your stuff's going to. So that's all the same. Now, in our program at Davis, y'all have dealt with probably process flow diagrams, or maybe even like higher level IO diagrams in some of your classes. And so you might be used to seeing something like, let's just say we have a reactor, horribly drawn reactor, and you have a stream in. You might say it's at like 320 Kelvin, and then you'd have 20 kilomoles per hour, and then you'd have like a percent composition of your components going in, and then same thing coming out. And you might have a different temperature. Let's say this is an exothermic reaction, and this is there's no temperature control in the reactor, right? And you're generating stuff. But you call all these out. So this kind of thing that we're used to seeing, you don't usually call out flow rates and temperatures of a product stream on a P&ID, or even operational parameters. What you do call out is going into our example again. If we have a distillation column, and you have this line coming in, there's going to be a coding system that tells you the sizing of this pipe. So let's say, it's 2-inch. You can just call it like schedule 40 pipe. And then what else would be? You'd have the reference arrow calling out where this is from. And that's usually kind of it for what you actually call out for that pipe. You just want to know what the pipe is and where it comes from, but you don't really specify what the product stream is, because anytime this gets reworked, if your product stream changes or a regulatory agency is coming in and they see that spec is called out and you're not meeting that spec, then all of a sudden you have to do drawing updates and it becomes a big nightmare. So the purpose of a P&ID is really to call out, like, hardware wise, what do I have available to me? And then for utilities, so again, let's say you have a reboiler at the bottom of this column. It's a beautiful kettle reboiler. So you got steam coming in. You would call out whatever this is. So let's say I'm trying to think of a reasonable number, maybe 200 pound steam. And it's kind of interesting in process operations. Usually they call out the pressure of the steam as the spec rather than like temperature when it's being used in this type of capacity. And then it'll have a return going somewhere that's referenced. Okay, so that's that's kind of how, oh, and this would also, this line would have some spec on it, you know, like 3-inch schedule 40. I don't know if that's even reasonable. Where was I going to go with that? So that's kind of how you call out your piping. And then on all of these, all your unit ops, so let's say you have a pump like that that's feeding our distillation column. I need to stop redrawing this and just stick with one drawing. Okay, so you would pretty much just start numbering this in, or tagging this equipment with the drawing number. So it becomes really important when you're making these that you follow some kind of numbering convention. So your drawing might be drawing 6011, just making that up. Well, this would now be P6011-1 because it's the first pump on here and it's drawing 6011. And this would be, this column would be C6011-1, and so on and so forth. And so that's usually how unit ops in a P&ID are labeled. So why is this important? Well, as a process engineer, if you go kind of a traditional route, especially like petrochem, pharma, anything like that, you're going to be dealing with these types of drawings, and you need to be able to read them. You need to be able to pull the pertinent info from them, and kind of be able to look at this and interpret it into a process of what's going on. So far we've talked about the piping. The other key aspect of this is the instrumentation. So let's say you have a tops stream from here. You might control that flow rate with a valve. And so this symbol, this is a regulator valve. So that basically controls the downstream pressure here. You might have a temperature probe on here. Oof, that's bad. Okay, I'm gonna blow that up. Apologies for my bad handwriting. So the way you draw an instrument is you just, off your line, pretend like this is your process line here. Off of here, you just draw a little line and you draw your bubble. And so if you have a temperature gauge, that would be a TI, temperature indicator, and then whatever number it is. So we'll just call that 101. And then if this is this is attached to an actual probe, off that probe, you might have some kind of transmitter, which you draw like this, and that would be a TT 101. And the reason you're drawing this box here indicates that it goes to your control system. And then you would draw a dashed line like this to show that it's going off to your control system. And then you would either in this call out like this goes to SCADA, or you would call out the drawing number in your control systems diagram that this actually goes to. And so this here shows you kind of where that bridge between the physical world of your piping and your pumps and your instrumentation meets our world that we've been talking about of your automated control system and your electrical diagrams and schematics. So as you're working maybe in internships or later on in your career, you'll kind of find examples of this, and hopefully it makes sense when you encounter it. I am working on trying to get example drawings of this, but as you may imagine, it's kind of hard because not everybody just wants to hand over their proprietary process drawings of how their plant operates. So I'm going to post up some materials on this if you guys want to get into this more on your own time. It's very useful depending on what kind of jobs you wind up doing. But for the rest of this quarter, we're not really going to focus on this much. What I am going to do is now switch over to some practical examples of how you would go about drawing this stuff in AutoCAD. Because if you guys are like me, you're probably working on Aspen simulations. I know some of you guys are in senior design right now, and I know junior year there were some classes where you had to generate diagrams of different processes. And so I personally actually used AutoCAD to do those drawings. And I'm currently using AutoCAD this quarter to do diagrams for my senior design. So this is an example of something I drew up. You guys can still see my screen, right, with AutoCAD?
Yeah.
Okay, awesome. So this is just something I drew up this quarter for our senior design that just summarizes all the key unit operations that we were doing, that we were simulating in Aspen, because as most of y'all know, if you've used Aspen yet, and you will use Aspen in the future, I'm trying to show you an example of why Aspen is not good for this. And it's so locked up because it's actually running iterations right now for the last hour and a half. So what you can see on my screen right now is a simulated process in Aspen that's currently locked up in computation. And as you can see, this is super ugly for diagramming purposes. Like, it's not easy to just look at and see exactly what's going on. And the lines are all crossed up and janky. So when you're doing an assignment where you have to summarize what you simulated in a nice and concise manner, drawing something like this helps clarify. And it's actually pretty easy. So if you guys want to fire up AutoCAD and follow along, I'm just going to go through real quick how I went about drawing some of this stuff up. So most of these icons are fairly common, fairly ubiquitous. You should have seen most of these before, depending on where you're at in the curriculum. If you haven't, you will. So I just want to show you how I went about drawing them so that you can use AutoCAD yourself to do these things. So go ahead and open up a new drawing. Now that we got that open, so you probably want to just go ahead and draw yourself a nice little boundary to start with. And this is where copying an existing drawing is good, because you already have your aspect ratio set in the layout pane. You don't have to mess with all that. You can just actually you can just basically copy paste this over and then whack all the content out of it. So I've now developed a library of symbols from that previous drawing that I can use going forward and just copy paste. But I'm going to show you how to start developing your own symbol library for what you want to do. So the first thing I want to draw is a heat exchanger. So I'm going to draw a circle. And this is going to be, I always get this backwards. So this is going to be a cooling heat exchanger. And so I'm going to draw a line here. I'm going to go just off the center of this. I'm going to go just above that and go down this way. Okay, and then I'm going to draw a line straight through the center, and then I'm going to go up this way. And if you have your specific angles on, it's pretty easy to draw that. Now, like I said, this is going to be a cooling heat exchanger, or a cooling unit. So the arrow goes up because up means colder, right? This always confuses me. And then you just draw, oh wait, shoot. No. So if you just draw one side of the arrow to make it symmetric, you can select that and then mirror. and you just mirror along that line that you drew. Oh, that's super annoying.
So does the up arrow meaning it gets cooler, is that because the process gets cooler and the heat exchanger fluid gets hotter? And that's what the arrow represents? Okay.
I think that's why. Like I said, this has always driven me absolutely nuts because it doesn't make any sense to me. That's super annoying. This isn't working the way I want it to. So I'm just going to mirror down the whole line, actually. There we go. I hate this command. For whatever reason, I can never, ever remember that you have to tell it, no, don't delete the stuff whenever you're mirroring. Don't ask me why. Okay, so now we got our little arrow. You can actually close that off if you want, but you don't have to. So that's our cooling heat exchanger. And as Sam said, I think it's because your process cooling water gets hotter as it goes through there. And that's why the convention is to have the arrow up. Now, if this is a heater, so I'm going to copy this, just use Control-C, Control-V. If this is a heater, I can then just rotate it around the center line, 180. So I just select it, type rotate, select the center, and then type 180. And now it's basically mirrored. So you could use the mirror command too if you wanted, but I just think rotate's easier. Okay, so now I have a cooler and a heater available. And I can put those on my lines wherever I want. Now to draw like a reactor or something, start with your handy dandy rectangle. I want to make this, since this is a reactor, I'm going to make it pretty squat. So I'll just draw a rectangle, and then I'll come in here to arc, and I'll do, there's a bunch of different arc options. I like to usually use start, center, and end. And so what I'm going to do is go start on the corner, center it on the midpoint for this, and then, ooh, that's annoying. That did not work the way I wanted it to. Did I get the wrong thing? Try that. You know what? I'm going to try it from the opposite side. So I'm going to go start, center. There we go. Okay, that's the wrong one. Bear with me. I'm trying to remember. I thought that's what I used before. This is what I used before. Okay, so you go start on one corner, go to the other corner, and then just drag up for whatever you want your radius to be. And this part gets kind of funky. But basically, just find a point you like, how domed you want that end, just by dragging your mouse back and forth. So I like it right about there. That looks pretty good. Okay, so now I have the top side of my reactor rounded off, and I'm just gonna mirror that across the center line of the reactor to get it on the bottom. So now I have nice rounded top and bottom for my vessel. I'm going to select the whole thing and do a trim. And then you can trim out the center lines. The other thing you can do is, if this is like a multi-tube reactor, you can draw lines through that center section. And what you do is, so here I drew a center line by selecting the center of this bottom line and drawing it across. And then now I want to divide one of these halves into more pieces. So I'm going to draw another line across the top of that top line. and basically divide it in half. So now I have a line running from this center line to the edge that I can then select the center of, go down, do that same thing again, and then draw another line. And then come over here, do the same thing on this side, and draw another line. And then I can go ahead and mirror this across the center line of the reactor, this whole side. So no, don't delete. And now I have a nice multi-tube reactor shown here. So if you kind of followed what I was doing with the lines, I was basically just really rapidly going through and dividing that up, keep dividing it in half till I get the number of lines I want representing the tubes. That's just a really quick way to kind of draw reference lines as you're drawing rather than going into a reference layer. You could do a reference layer to break it up, but honestly, like you can't see the multiple lines because they're all laid right across the top of each other. So if you go to highlight, you can see there's a bunch of lines shown there. Let me zoom in a little bit more. You're gonna see it's thicker at each one of those points as you go across here because there's multiple lines laid over the top of each other. But if you're just looking at the drawing like this, you can't see that there's multiple lines there, so it doesn't matter. Okay, so now I have my reactor. I have a couple of unit ops. I want to grab this arrow and just copy it. And then, actually, you know what? I'm just going to redraw the arrow. Never mind, delete that. So you need arrows to symbolize your piping. So I'm going to just draw a line up off of here. Draw a arrow on an arc here. You can use whatever angle you like. I like this angle right here, which is a 45. And again, you can mirror that line if it doesn't freeze up. You can mirror that about this line to make that arrowhead symmetric. And then you can just keep drawing lines off of that. Okay, so I got my top coming into my reactor, my feed line, and then I'll just draw an arrow for the bottom side. And then rather than just drawing a line for the bottom side, I'm going to delete that, and I'm going to copy this arrow, grab the tail, drop it onto this point, and then to make it turn, I'm going to just do a rotate. And you can just you can actually just click and drag to rotate, or you can tell it the angle to rotate through. But one thing I want to point out is if you look at the cursor, it's got a little whoop-de-doo arrow showing the angle of rotation. And that's important to know because if you are going to type in the angle of rotation, you want to know if it's going clockwise or counterclockwise. And I always get this wrong. So I want to say it's always counterclockwise, and I think that's what that arrow is representing. So let's test it and see. I was right. So I told it to go 90, and it went 90 degrees counterclockwise. So that's good to know. Okay. So let's assume this reactor has an exothermic reaction, so it's coming out hot. So I'm going to grab my handy dandy little heat exchanger and type move and move it over here and slap it on. And then I'm going to grab my arrow again, and I'm going to copy it, coming out of that heat exchanger. And then the next thing we probably need is some piping or a pump to pump it through some piping because you're going to get, you have frictional losses in your piping. So you actually have to impel things through your piping. So that's a good thing to draw. So grab a circle again, make it about yay big because we're gonna draw a turbine pump, a centrifugal pump. So draw an inner circle, or draw an outer circle, and then an inner circle, and then you're gonna come here and just draw some lines. So it wants to snap onto that for some reason. That's okay. We're gonna move away from the other stuff so that we can see to draw and it doesn't keep trying to snap onto other stuff. Okay, so draw a line from the top and then down and then over here. And then we're gonna trim this piece out. That looks a little chunky. I'll shorten that up. Yeah, that looks better. Okay, and then we're just gonna fix those lines there so they're not overextended again. Yeah, that looks better. All right, and then we need to draw the little base. So come off here, go like that, hit the center line. That's half a base. And then I'm gonna mirror again. I'm just gonna go from here to here along the center line. Bam, now I have a centrifugal pump. So you'll notice in here, a lot of these operations I'm doing, I'm drawing half of it and then mirroring. The reason for that is when you're drawing angles and stuff, it's much easier to just draw the half you want and then copy it than it is to come down here and like draw that line on the angle and stick it here and then exactly mirror it on the other side, because you need to know exactly what length that bottom edge is. And if you don't hit that precisely by eyeballing it, then your angles are off and this thing looks all janky. So it's much easier to just draw half of it and then mirror it. Okay, so now I have a good looking pump. I'm gonna move that. I'm gonna select this outer edge and throw it onto the arrow. And then I can show another arrow coming out of that guy. Cool. So now I have a reactor with a stream coming in, and then it's being cooled and then going into a pump. So what else? Other than that, I mean, you guys can kind of see how I created that. So you would create columns in the exact same way you would create a reactor, just with different ratios. The reboilers are a little bit more tricky, but it's basically the exact same process as the reactor. A compressor is just, I can show you super quick how you do the compressors. So you just go line up, angled line up, line down. Make sure you hit that center line. Cool, that looks good. And then mirror that you just drew. And now you have a compressor that's way too big. So you grab it and you scale it to be, let's say, 30% of what it was. Cool, that looks like a good size. That aspect ratio is a little funky, but you can recreate that however you want. So what I'm showing you is just that whatever shape you want to get out of here, you should be able to figure out how to draw it after a little bit of practice. You should be able to figure that out pretty quick. And so you can take any flow sheet in Aspen and fairly quickly draw it in AutoCAD and get what you're looking for. So the last thing that's important for this is drawing in text. So in the top tool ribbon, you can see there's the text option. Just click, drag where you want your box to be, and then type in your text. Actually, let's make this reactor 1. Okay, now you got text. Now this is a little bit small. So if you double click on your text, you'll notice that the ribbon changes up here. And there's different text you can select in here, but really I usually just use the default. The default's to Arial. And you can change the sizing by changing the text height. So rather than selecting a font, you're basically just setting a physical scale for your text. And so right now this is too small. So I'm going to change this to like 0.5. Okay, that looks pretty good. It's maybe a little bit big, so I'm going to change it down to 0.4. Cool, that looks pretty good. And then I can drag that in here, and you can put your text for something inside or on the outside next to it. It's really kind of up to you. If you're doing P&IDs, then this would be a P&ID tag, which would be like R101 or something like that. But that's easy. You can make your text whatever you want. And then you can do the same thing to just label your streams. So you could call this, again, you can call it whatever you want. Why will you not let me edit you? So we can call this one R101 feed. And then if you're doing a detailed drawing where you're calling out your process specifications, you can just say 320 Kelvin. And then 50%. Let's say this is 50% methanol, 25% water, and then 25% of who the heck knows what. There is a way to do subscripts in text, but it's a little bit complicated. So if you guys are interested in that, I can post something on Canvas of how to do it. It's just a little bit more involved. It's kind of pain in the butt, and I don't remember how to do it off the top of my head, so I don't want to make an even bigger fool of myself trying to show you how exactly to do that. But there is a way. So that's how you create process flow diagrams. It's honestly, I think this is the best tool for it. I know you can use things like Lucidchart or like even Visio that are fairly straightforward, but my personal preference is just to use CAD because it keeps me in practice, and I feel like I have the most control over things. Some of those other flow charting tools, you know, they don't allow you to draw your own blocks, so you're kind of stuck with whatever they have available, which I don't like. And sometimes the snapping will get funky. So I don't know why I'm trying to like preach and convince you to use CAD. You can make up your own mind on that, but I usually try to draw stuff in CAD for all those reasons. So we got 10 minutes left. Anybody have questions about what we just covered or what I went through super fast?
So if we were to do this for our PLC, it would just be really small, right? Would it just be like a motor?
Oh, yeah. So just so we're clear, like this isn't probably something we'll be doing for our PLC system. This is something I just wanted to cover for you guys, so you kind of, or at least willing to consider making this kind of diagram for classes in the Chem E program. So I did diagramming in CAD mostly for the senior design classes, but like you might use this for some of the lab classes, like diagramming and distillation column. So anyway, to answer Mason's question, yeah, I mean, for us, this would be pretty simple. So like for our PLC system, yeah, it would pretty much be like a motor. Oof, that was way too big. You just kind of have a motor and then a dashed line. And then like your VFD, and then that would connect to your PLC. And obviously you would do this pretty and nice looking. But yeah, pretty much that's what you're looking at for our system. And then you can make these, where is it? Dang it, why is this not showing up? Oh, it's not available in this drawing. But yeah, you would want to make these, lines dashed just to show that they're like communications connections. But yeah, this would pretty much be the extent of our P&ID. And even this is like overly detailed for a P&ID because really like, this isn't really instrumentation, it's controls.
At least for, go ahead, sorry.
I was just said thank you.
Everything? What's up,
I
Evan?
heard that, what's up?
I was saying, Evan, what's up?
Yeah, I heard Professor White said you could also use Chem CAD. Is that like another source for just modeling the?
Yeah, I've never used Chem CAD before.
Me either.
I didn't know it was free. Oh, that's the one from ChemStation, right?
I think so.
Interesting. Yeah, I mean, I know that's a powerful tool. I think it does more than just diagramming. I've never used it before though. I will say, you know, there are tools out there that are definitely more user-friendly and intuitive than AutoCAD. AutoCAD's, you know, built up from a very old program, so in some senses it's archaic and clunky. The reason we're covering it here is because it's kind of standard across all industries. Like almost all companies have at least somebody that uses AutoCAD just because it's kind of like the ubiquitous standard. And when they're not using AutoCAD, they're still using DWG formats from other programs like Bentley or BricsCAD, just off the top of my head. So, I mean, that being said, yeah, you could totally use ChemCAD. The reason I encourage you to use AutoCAD is just for the practice. In my opinion, you're going to spend about the same amount of time as you would using some other software, and you get a little bit of practice clicking around in AutoCAD.
I agree.
I feel betrayed that Dr. White would recommend something besides AutoCAD. No, I'm just kidding. It makes sense for him to recommend that because it's probably more accessible to people who aren't, you know, doing something like this.
Cue Jeopardy music.
Any questions? Okay.
So I actually have one. It's more in general than specifically about this. So any of the stuff that we've done so far, how much do we actually do in the Chem E curriculum?
Are you talking about today?
Just like this course in general?
This course in general, I would say what we covered today is probably the most directly applicable to our curriculum. So this course is kind of intended to augment our curriculum at Davis because, in my opinion, they do us a little bit of a disservice by not having labs on automated control systems, not requiring any kind of CAD or 3D modeling. That being said, there's a lot of jobs in chemical engineering where you don't really need to know AutoCAD, and you may or may not ever actually program an automated system. But I just think it helps, like doing PLC ladder logic programming, it helps in context understand automated control systems. So you'll take, what is it? Is it 157? This controls? Guys, help me out here.
Yeah, sorry, I know I'm like the only
You're fine, man.
first year here.
Yeah, you're fine. So 157 is control systems. Okay, somebody's in the chat. They're gonna save me because I should know this. Yeah, process controls. And so that class deals with basically what you do is you kind of get like a high level model of your control system where you're like, this is what I'm measuring going to have an algorithm that goes through a feedback loop, and you're modeling it mathematically from kind of like a really high level, right? And so what I'm hoping to do is actually get a guest lecture from Professor Ellis on P&ID control, which is mostly what you focus on in that class, because you can implement that in our Click PLC, even though it's super simple. Like, it does control loops, which is what you spend the entire quarter talking about in that class. So there's a connection there. But in that class, there's no lab portion, so you never actually go and program these things. You just solve mathematical systems on paper. Otherwise, I would say you do very little circuits. There is an attempt at covering some instrumentation fundamentals in some of the labs. So for example, one of the labs where you're measuring temperature using a thermocouple involves like changing the sampling rate in the software for the thermocouple. And so, spoiler alert, one of the things you'll find is that if you set the sample rate to be 60 hertz or 60 times a second, you get really clean data, because if you have power to a system that's cycling at 60 hertz and you're sampling at 60 hertz, then your sample is always taken at the same point in the power wave that's coming in, and so you don't get any distortion in your signal. So concepts like that are kind of briefly covered in our curriculum, but they don't really go into a whole lot of detail in it, and it seems like they kind of hope you'll figure it out on your own. So hopefully in a very long-winded way, that kind of answers your question.
Yeah, definitely. Thank you.
Yeah. So what I'm hoping is that this augments what you're covering in the curriculum, and maybe helps expand your understanding a little bit. And then also for stuff like this, gives you a tool that you can use, because in your reports, you're going to need to draw diagrams, and you can hopefully bang that up pretty quick in AutoCAD. I gotta clean my stuff. It's getting all dusty out in the garage. All right, anything else, guys? I think we might actually end on time this time. How's that, Andrew? Okay, so very nice. So for homework, I think what I'm gonna do is make your own process flow diagram, be that for a class you're currently taking, or just make something up. Just make 2 unit operations, some arrows and some labels. It's not gonna be super complicated. But this way, at least you'll have to create a unit op from scratch, and you'll get practice with the arrows. And then I'm going to assign a little programming assignment in Click software, which is going to be basically write a program where you use a push button to turn on a light, and it latches that light on, and then it requires, and then you can hit another push button to unlatch the light being on and turn the light off. So this is Bill covered how to do this in his presentation, but I'm just going to give you a verbal description. It requires a normally open contact in series with a normally closed contact, and then that first normally open contact is going to be in parallel with an output, and that's basically how you're going to latch it. And so you're going to have a little you're going to have a contact on your rung that is your output that turns on the light. And so basically, when you hit that button to close the normally open contact, it energizes the output, which is feeding into the circuit that energizes the output. And so it's basically, it keeps itself energized until you break the circuit. So that's your verbal description. I'll write that in the homework assignment, but if I draw it, it'll be super obvious how to program it and you won't have to think about it at all. So if you get stuck or can't figure it out, you can ping me, or you can go back and look at Bill's presentation, because I think it's fairly early on in there. But it's kind of a cool little programming gizmo, and it should help get you thinking about how to take advantage of what Bill was talking about cycle time of execution. Thanks for coming. Hope you had a good time today. I'm going to kill the recording.
Last quick.
Oh yeah, go ahead, man.
Are those 2 separate homeworks or just one?
I'll probably make them 2 separate assignments.
Got you.
If that's cool with everybody. Cool. I'm going to stop the recording.